Okay, so maybe I'll start. Okay, so maybe a word of introduction. My name is Jan, and I'm running the colors of GFT Poland, this company that's doing consulting services. So in that capacity, I'm currently working as a Scala team and tech lead for one of our customers, doing some boring stuff, financial stuff. It's totally boring. But what's interesting is in Scala. So as I looked through the code base, which has some significant size, okay, I found different idioms, programming idioms. Okay, so varying from immediate mutation to it's like highly monadic, pure functional style. And as the highly monadic, pure functional style is the hype of the day, okay, everyone talks about that. I wanted to evaluate the performance of this code, okay, so of different ways, different styles of writing code and still being in functional genre. So, okay, doesn't work too well. This doesn't work too. No, because this is not the right direction. Okay, so I will give you some examples in Haskell, Scala, and C++. Okay, I will be benchmarking them. I have benchmarked them on a single machine. Okay, so it doesn't matter what kind of machine it was. It was running Windows 7 just by accident because I had such a machine handy. Basically, we are interested in the baseline, so in the difference of performance between different programming, different functional programming styles. Okay. So benchmarking Scala is really difficult, okay? Because first of all, benchmarking Java is very difficult. So there's this nice library called JMH to do it, and someone, actually Konrad Malawski, for which I'm very thankful, wrote a port adapter for it to Scala. Okay, so I'm running Scala 2.10.4, very recent, Java 1.70 something, and JMH 1.5. For Haskell, benchmarking is even more difficult because it's a lazy language, okay? But there is a nice library for that, written by Brian O'Sullivan, which is called Criterion, and it's really nice. I'm running Haskell GHC 7.8.3, and I'm combining with the optimize option because I want everything optimized and optimal and as fast as possible because it's slow. Okay, but I'm maybe a bit ahead of what I want to show you. So I also ran some C++ examples. No benchmarking harnesses there, just wall clock time. So really old style. I'm using MinG W481 and GCC 4. It doesn't matter. I'm running on Windows. This matters because, in fact, if you run those examples on Linux, you might get a bit different ratios between C++ and the rest of the stuff. I'm not going to go into details. Anyway, you'd have to find it out in the internet. Okay, so if you want the code, the real thing, just go to this repository and you'll get it's some random name, okay, on GitHub. Okay, so before I really begin, so the rationale for my thinking was I looked into the code, I looked into the source code. There were different programming styles. Then, like a month ago, there was a guy who really completely ridiculed this whole big data industry by running some, some MapReduce, it's called MapReduce, or some graph algorithm on his laptop, and on one thread he ran like 100 times faster than a 128 cores Hadoop cluster or some other nice Spark library. But he cheated. He cheated one important way. So he used an algorithm which is highly mutating and is not very easily distributable. Okay, so it was a trick. Okay, so I started thinking, okay, so what is really the relative performance of such solution, like imperative solution against functional solution? And the other thing is, if there are those nice languages like Haskell, where you can do only pure functional programming. So if you want to cheat, you have to use something called IO monad or ST monad. So if you go to the LVS shootout benchmarking game, you'll see very fast Haskell programs, which are in fact imperative programs running in an ST monad, which is a trick. Okay, which is a trick. The problem is, okay, it's fast, it's pure functional, but it's pure functional in a name, because everyone says that pure functional programming is cool because you get the correctness of the programs for free. So you get you look at the program and you see that the program is really correct. Okay, so let's start with merge sort. So I took as examples sorting algorithms: 3, merge sort, quicksort. Okay, quicksort is quick, supposedly, and then heapsort. Okay, so let's start with merge sort. Merge sort is just folklore. Everyone knows it. No one knows who discovered it. Knuth believes that it was von Neumann around 1945, but actually we don't know. So everyone knows it. Everyone could discover it. It's obviously correct. So merge sort is a very simple algorithm. You just divide in half, divide in half, divide in half, and then merge, 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 and you get a sorted sequence. Has a nice functional implementation. Okay, it's easy to implement functionally. Difficult to implement with mutation. Works well with lists, tapes, like old style tapes, sequential data, lists. Yeah, lists are tapes, and it's very fast in asymptotic terms. So if you could ask a theoretician, like computer science theoretician, who runs a totally unreal model of computation like a RAM machine, okay, he would tell you that a history ends at merge sort because you cannot go faster than O n log n, and that's it. Okay, so we're fine. Cons may be slower than quicksort, okay, but the quicksort will be discovered like 15 years later, so no one cares about that. Okay, so let's take a look at a merge sort. Okay. This is just a run of sources for examples. I didn't write it myself. I just took curated examples from the internet. Okay, these are either public domain, MIT, or Creative Commons by attribution, like the Stack Overflows, or examples ICC by attribution. Okay, so Haskell, C++. Generic Scala. I took like programming in Scala example improved by someone to actually work. Okay, good. So let's start with Haskell. Merge sort is really nice. This is merge sort. Merge sort does just merge. Okay, so you have this merge. Predicate is just the technicality. Okay, merge sort merges two things where the list is done with split. Okay. This is some clever way of splitting with going only once through the list, so it's supposed to be very fast. And the merge is just the list merge, okay? You could just say split at n, but then you would have to figure out what n is, and in order to find out what n is, you would have to go through the whole list, because Haskell doesn't store it for you, because it's pure functional, and this is verboten in Haskell, okay, to store anything. Okay, so this is actually, I'm just showing you this code not to tell you what's inside of this code, because I really don't care. I just want you to take a look at this code. It's pretty simple, okay? You could understand that easily, and you could be fairly confident that it works, okay? So bottom-up merge sort in Haskell, some believe it might be faster because it just goes bottom-up, so it just list comprehension to split the list, and just go bottom-up to get all the work done. No double recursion, should be faster, might be faster. Okay, let's see the benchmark. Okay, you can do it also in C++, and this is actually a nice one, because in C++ actually we have a standard library, okay, to talk of, okay? So this standard library makes our lives easy. So I have in-place merge, I have standard merge, in-place merge, what you want. Of course, I'm implementing this in in terms of type classes. Random access iterator is a type class, as you'll see now in my iterator traits. Random access iterator value type. So a nice type class, although syntax is really not nice, because it's some like evolutionary extension of something coming from the early 90s. Okay, not as nice as, say, Scala. Okay, merge sort in Scala. Really easy. Now I'm doing this trick. I'm just taking the length of the list here. Okay, I'm splitting add. Might not be as fast. Maybe should not be as fast. But it's fairly comprehensible what we have here. Okay, and benchmark times. Okay, so let's see. Well, C++ is really fast. Okay. Maybe because in-place merge is really fast, and maybe it's something optimized because it's in the standard library. Haskell bottom-up is really faster than top-down, but not much. Times in milliseconds. So to sort 1 million records, you're taking 5 seconds on a pretty recent hardware. Okay, pretty recent hardware. 5 seconds for sorting million of integers. This is really, I mean, this is sorry state of things. This is really slow, abysmally slow, as we will see in a moment. Okay, and Scala is, well, quite fast, 1 second, okay? C++ is really fast, but maybe it does something behind the scenes, which is mutation, okay? And then let's go to Quicksort, okay? Quicksort is quick, but it's not quick in terms of abstraction, okay? It's really quick, okay? So it's something like kind of a taboo in theoretical computer science. Just write something that works, okay? It's really difficult to publish such results because no one really actually wants to see those results published, okay? Hoare did it, this guy, okay? He took a break from theoretical science, did some real programming around 1960, but everyone said, okay, you've shown us this quicksort, but we don't believe you that this quicksort is actually quick. No, they believed him because he had numbers. But they said, oh, we don't know if it sorts. So Hoare spent like 9 years inventing Hoare logic to prove that it actually sorts. And Hoare logic is actually something with which we can prove programs, okay? He wrote another article with logician extending Hoare logic, and then Wirth wrote a book in which he's shown how to prove algorithms. So it's really a done thing. You don't need a cog or address for that. But of course, it would be nice and more functional. Okay, let's say Quicksort is quick. And but you cannot implement it functionally, okay? You cannot. It's impossible, okay? Because it needs mutation to work, okay? So it doesn't work well with lists. Once random access demands mutation, okay? And nobody knows what it does, okay? So these are just code samples. It's like this is something I'm going to talk about the st monad for Scala. It's just some code from excellent book, Functional Programming in Scala, by Paul Cisana and Runa Bjarnason. Okay, so this is ugly standard Quicksort with a bug, taken from Odersky's Scala by example. Okay, very nice. So you see this magic here, imperative, impure magic being done. There is a bug hidden in here. But this bug was in most of Quicksort programs, in 20 years. It took 20 years for people to discover this bug, okay? But it is there, okay? And, well, good. So this is in Scala. You don't trust it, okay? So let's go to Haskell, okay? Haskell is pure, is functional, is perfect. So if I want to write it in Haskell, I go to stmonad and I get that, okay? It's functional programming. It should be obvious that it's correct, that it's working, it does what it does, but it's not. This is the point. It's even harder to see what it does than in standard impure language, okay? So actually, to be sure that it works, we have to prove it. We have to go to some logic, give some assertions, like invariants, which require a living person to prove it, okay? Okay, nice. Then we have the same thing with Scala. We use the Scala's library, which is a library, not a compiler. Haskell has a compiler. And it's even more ugly, okay? It's not my example, even more ugly, but maybe it's fast, okay? And this is functional Quicksort. This is a very nice program, but it's not Quicksort, okay? Because Quicksort has to sort in place, okay? So it demands mutation, but it's obviously correct. In fact, I will tell you, this is a kind of merge sort, but it's clever merge sort. It doesn't split in half, but it splits the smaller ones into smaller ones and bigger ones, and then runs merge. Okay? And let's see let's see. Okay, this is functional sort in Scala, also taken from Scala by example, and this is functional Quicksort in C++. Okay, syntax is ugly, but it's really functional. It's immutable, returns copying, everything's copying. You can be sure that it kind of works. And these are times. What is really interesting, so it's like imperative sorts millions of records, like in 112 milliseconds, okay? So if you do functional, you're going to be 20 times slower, okay? stmonad doesn't work for Scala because it's part of a library. So we have problems, real world problems with garbage collector. So it just never finishes, like, okay, never being 13 seconds. So it's abysmally slow. And, well, so you can see yourself that C++ functional is also very slow because functional is slow. This is a problem. It does a lot of consing. It was called consing in the 70s. Okay, because it's a term from Lisp, and this is why Lisp lost. Okay, this is why functional programming hasn't become more popular, because it has to do consing. It has to be slower. This is a problem. Okay, so like pure functional algorithms, or if you use stmonad, in fact you're getting impure algorithms. So you could do mutation. You could do mutation. Scala does mutation standard library. SML, OCaml will do mutation. Okay, so how to make sure? Okay, I'm gonna skip the heapsort because it just shows some immutable data structures running out of time. So I just wanted to show you that actually heapsort. Using immutable data structures like Scala as a heap or Haskell PQ or heap, these are both immutable data structures, is kind of really slow. Scala priority queue, which is mutable data structure, is way faster, okay? Because we can do mutation. But what is interesting, we are doing something mutable here. So you see here, we are using mutable data structure. We are using even maybe var. No, we are not, but we are mutating inside the priority queue. But it doesn't get outside of it, okay? And this is something I'm really thinking is the important takeaway from this. Because it doesn't matter if you are doing functional programming. If you are doing functional programming, you're doing it. If you're doing it in such a way that you have a function that doesn't do side effects outside of the world, okay, you still can check its properties, like using quick check in Haskell, to be sure, kind of maybe not sure, but with some probability to see that it does what it's supposed to do. So you shouldn't be afraid of mutation in language. Okay, in your functional programming language, that it does mutation, that it allows mutation, like Scala, like F#, okay? Just mutate, okay? Don't go outside of the function and test the function as a whole, and you should be fine. The other alternatives are really non-existent, because stmonad is exactly that, and functional approach, like standard functional approach of doing, it's like those nice functions where only copying is allowed, okay, is slow, is logarithm n times slower. There was even a paper on that in the 70s, I believe, late 70s, early 80s. Okay, this is the first time where functional programming lost. Okay, so these are mainly takeaways. Imperative constructs win in terms of performance. Haskell seems to be faster than Scala and C++ for pure functional constructs. You would notice that if you would run through those results in detail, because Haskell is very heavily optimized towards functional programming. Garbage is a problem in functional languages, okay? It's really a problem. Scala is a library, so it's way slower than Haskell, which does many things as a compiler. Pragmatic functional languages accept that mutation can be a fact of life, and you should too. You can isolate mutation and test it, okay? Monads are not perfect, because imperative code in monads is even less readable, and if it has functional interface, test it, and you can be certain to some extent that it really works, okay? And these are nice books. I've also taken some examples from, it's like the first two are really nice, okay? I think that's it. Some questions? Yes, please. Okay, maybe. Yeah. Okay, that's gonna work.
Haskell is lazy language. What would happen if, if we would get rid of laziness in Haskell? Would it be much faster?
No, actually, laziness makes Haskell potentially faster. So Okazaki writes about that in his exposition of leftist trees, leftist heaps. That in fact, if you have laziness and you don't look inside of the data structure, you get amortized cost of O(n) instead of O(n) log n. Okay, this might be the reason why, for instance, a functional quicksort in Scala using vector, which is actually an Okazaki leftist heap, it runs a bit faster than an array because it can amortize the cost. But the problem is, if you would like to use it in this way, in this capacity, then you would lose this performance, because as soon as you, like in an example of Schrodinger's cat, okay, if you take a look at what's inside, you're losing the performance, okay, because side effect is going runs outside of the monad, the monad being, of course, the Haskell runtime environment, lazy Haskell. It's a monad, in fact, yeah. Okay.
No more questions? Okay, so thank you again.
Thank you very much. Many thanks. I really appreciate that you stayed so late. Thank you.
Okay, thank you for joining us on this research track.